The hash join is another important join algorithm. In order to illustrate it, let's have a look at these two tables, employee and phone. So we have the name of the employees of a company and the phone numbers. And obviously, or in this case, we will use the ID column to make the join. That means we want to join, for instance, here this tuple with 10 and Jim with 110 and Jim to see that Jim's phone number is 110 and so on, right? Now the idea behind the hash join is to use a hash function to create partitions of the individual relations. Let's say we use the hash function modulo 3. So we take the ID, so hash of x would be x modulo 3. So we take the ID, for instance 10, 13 and so on, apply the hash function, and then what the hash function will give us 3 buckets where the IDs are in that have the hash function output 0, 1 or 2. Right? And the same we have here for the phone as well. 0, 1 and 2. Now the observation is that it is sufficient to compute the join between these two tables by computing the join between partition 0 and partition 0, between partition 1 and partition 1, and between partition 2 and partition 2. Here in the illustration you see the real values from before and the hash function that maps x to x modulo 3. And you see we have results for the individual partition joinings, and overall, if you're looking at all of these result tuples, this will be the correct result of our overall join between the two tables. Now in order that this is correct, it has to be ensured that if there's a tuple, let's say here, that this tuple, 15 and Pete, will find a potential, or will find a join partner only here, if the join partner exists. It's of course okay if there's no join partner. Well, then there is no result tuple involving Pete and 15. But if there's a join partner in the initial phone table, it has to be exactly here, right? In this circled partition of the phone relation. It cannot be here and it cannot be here. If it was here or here somewhere, then 15 and Pete would not find this join partner, hence the result would not be correct. Yeah. Luckily, it is not difficult to choose hash functions, just as we did with modulo 3, that have the property that we can compute the global join by making these joins of the individual partitions. So again, the idea behind hash join is take a hash function, look at the join attributes, and hash the tuples according to the join attributes. Then these partitions, consisting of tuples that have the same hash function output, should be small enough that they fit into memory. And then, if we have two partitions for one and the other relation, like employee 0 and phone 0, then we will go and make a match between the two. Yeah, that means we join these two relations. It does these two partitions. It does not mean that we go and take this tuple here and match it with all the tuples here. No, we will still compute a join here. If you go back one slide, you see that even though these two tuples are in the employee 0 and these are in the phone 0 partition, they're not per se a match. We still have to go and match, right? We will not match Dave with this one or that one. We will only make a senseful, meaningful match between here the tuples that correspond or that match according to the ID, right? So you'll partition and then we will join. Here you see the pseudocode of the so-called Gray's hash join, how it's called in literature. So what we do here, like exactly what we have described earlier, we partition table R in k partitions. We call these partitions Ri. And we do this the following way. We walk through the entire relation. We hash this tuple according to the join attribute. and then we put it to a buffer page, a block, and then we create this way. We have one buffer block per hash value output, and then in the end we can write these individual partitions to disk. The same we do also for partition for relation S. We create partitions Si the same way. We apply the hash function on the join attributes of this tuple S, and we add it to a buffer page according to this hash function output. And then this way we have in the end these partitions Ri on disk and the tuples Si as well, right? So now we have to compute a join between these individual partitions, and again, like as we just discussed in the example, we will of course make a join only between these partitions that have the same hash function output, right? So obviously it has to be the same hash function here. So how does this work? This is the so-called probing phase. We have k partitions created before. So now we do for all of these different partitions, we go through them one after the other. The parameter that is denoting the current partition to look at is called L. So for all L from 1 to k, we do the following. We read partition RL, and we create an in-memory hash table using a hash function h2. So now let me illustrate this. So we have now RL and SL we want to join, right? So now what this algorithm is doing here is to first of all go over all of the tuples R of RL and create an in-memory hash table that has again many, let's say here 5 hash buckets, and this is done using hash function h2, and then we go over all of the tuples of SL. As you can see here, we apply h2 on S, so we have a tuple S out of SL. We apply hash function on S, and then this comes here, and then we check if there is some matching R tuple in this hash bucket. And if there is a matching R tuple in this bucket, then we add the concatenation of R and S to our result. Then we empty these buckets and we continue with the next L. So now you're wondering, what is the hash function h2? Is it different than the hash function before that we used to create the partitions? And the answer is yes, it's different, and it's very important that it's different. Can you guess why? So what we want to do here, we want to make an efficient matchmaking in memory between the partition RL and SL. The tuples inside RL have been put there according to H, the hash function from the previous slide. And the same hash function, H, has been used to put the tuples of relation S into SL. That means that all the tuples in RL and all the tuples of SL have the same H value, the hash function value. So if you want to create now, in order to make an efficient matchmaking, these buckets here, and we use the same hash function H, we will have only one bucket. So there would not be any partitioning at all. So we could even leave that out at this step. So it wouldn't make any sense to apply H again here. And if we now use H2, a different hash function, then we can distribute the tuples in RL in a meaningful way across hash buckets in memory. And of course, then we have to also use H2 for the tuples in S, and then we can efficiently map them to this hash table and create join results. Yeah. So in principle, it's a very simple algorithm. The first idea is this was described on the previous slide, the first idea is to create partitions that fit into memory. Second phase, the probing phase, we want to now really compute the join between the individual partitions that match. Yeah, this is indicated here by the L parameter. So we want to join here RL with SL. And then we could also apply some different algorithm now, for instance, a nested loop join on RL and SL. But hashing is usually more effective, and in this case also we require to have a join which is like an equi-join in order to make this work. And then, of course, the natural choice would be to also use, for the probing phase, some hashing. So overall, we have seen 3 different types of algorithms for computing joins: nested loop and variance, right? In particular, the block nested loop join. The good thing about nested loop join is it works for all kinds of joins, but it can be very expensive, as we have seen. It's quadratic complexity because it enumerates the entire cross product. When I say it works for all kinds of joins, you have to be careful because we also looked at the index-based nested loop join, and there we required equality predicate. Then the merged join requires that the inputs are sorted. If not, we can sort them, but this comes, of course, at additional cost. Yeah. If we have a clustered index where the data is already accessible in a sorted fashion, cool, yeah, so we can use that. But again, note that if we have a non-clustered index, which somehow looks also that we can access sorted data, note again the discussion that accessing or reading large amounts of sorted data from a non-clustered index can be very expensive. Then last we looked at hash join, and as you probably guessed already, the good choice of a hash function is crucial. First of all, it has to make these partitions which fit in memory, and then second, it also has to you have to come up with a second hash function H2 in order to make the hash or the join computation over these hash partitions. So if you have a join which involves multiple attributes, that's not really a problem per se. So if you have the nested loop join anyway, no problem, right? You can have multiple attributes. You can have predicates which are more complicated than having just equality checks. So this is all fine here. Yeah? This is like the most powerful algorithm. It's also the most naive one because it would in principle essentially it computes the cross product and then filters out according to a predicate, P, or we call it zeta often, right? So it will work for everything, for multiple attributes, for all kinds of predicates. The merged join also works for multiple attributes. You can sort, but then it still requires the equality predicate to be used in the join. The hash function also works for multiple attributes the same way, but again, here we would also require equality. That means if you have now these options implemented in your database system and the user query comes in and the SQL query contains some predicate which is not equality, then the database system does not have the choice to select among all of these 3 algorithms, but it has to go and take the nested loop implementation. On the other hand, if you have equality predicate, then all of these options are possible, and then the database system has to decide which one is the cheapest according to different observations and statistics. For instance, do we have already the sorted data somewhere? And this is all the job of the database system, but we have to, of course, understand if you're writing a query with a like non-equality predicate, which is sometimes needed, then this is also a costly query because you cannot make any smart processing of the join. And lastly, I want to mention also again that if the join predicate is in a way that allows many join partners to be found, or the data looks like this, is essentially what can come out of a join computation is always the cross product, right? This is like the superset of all join results that are possible. It's always the cross product in the case where the data or the predicate looks funny. That means that even though you say it's a merge join or hash join and they are efficient, in the end, according to the data and the predicate, in the end they can also produce many output tuples. So it's not always the case that hash join is very efficient. It has to also depend on other things. And then also, if you think about that, can you think of an example where the nested loop join is more efficient than the merge join? What has to happen that this is true? Well, for instance, the extreme case would be you have one relation which is very tiny. Let's say it's only 1 or 2 tuples big, and the other one is very large and unsorted. So you have to sort it first, and then the cost for sorting this big one is higher than just applying the nested loop and going 2 times over the big relation, right? So you can construct, if you think carefully, you can construct always for the algorithm case situations where according to the data or the predicate, one is outperforming the other. Also, the one that is outperformed in this case would usually be named by people to be more efficient, like hash join and merge join. But there can be always corner cases, and this is like something you have to reflect yourself in order to really understand what's going on here. So of course, it's not only about joins, the database, but there are other operators as well. For instance, the very important selection operator, right? We denote with a sigma in relational algebra. We already briefly, when we talked about indices, we looked at situations when we can make use of an index and when not. And here the database system has to decide if the index is clustered or not clustered. Yeah, so what is the selectivity of this predicate that we're using here? And in worst case, we have to go for a full table scan. And how does the predicate look like? Is it a disjunction, conjunction, and so on? And all of this has to go into the database decision, how the selection should be implemented. And what is the cost of this implementation? Right? So if you have, for instance, a query, select something from table name, where, and then we have now a predicate, x smaller than 100, or name is Joe. Let's say we have an index on the name attribute, so we could go and check for Joes. Now, do we use this index? And the answer is no, we cannot use the index. Well, we can use it, but it will be of no good, because anyway we have to do a full scan because of the or, the disjunction, and the other predicate x smaller than 100. If we have a query predicate x smaller than 100 and, so a conjunction, name is Joe, then we can use the index on name, look up all tuples with name is Joe, and then iterate over them to find those that have x smaller than 100. And this is like something that the database system, or we have to understand in which circumstances one or the other choice is better. So we have more operators, duplicate elimination, aggregation. These were denoted like this in relational algebra. And how do you implement them? There are multiple options. We have already discussed on one example at the discussion on sorting, how you can implement duplicate elimination. Well, by sorting, so you're bringing tuples which have the same values close to each other, and then you can find them easily. But you can also implement duplicate elimination by hashing, because, well, similar or the same values will end up in the same buckets, and then you find them easily. And the interesting thing is that what you can do in terms of sorting and hashing to enable duplicate elimination, this will also work for aggregation, right? If you want to aggregate, and you have group by and aggregate, then the group by can also be realized by sorting, because the same values according to which you group by, for instance, a name, will be end up next to each other, and then you can simply aggregate. And for hashing, it's the same. The same numbers, the same values of name, for instance, if you say group by name, will be placed to the same hash buckets, and then you have them all together, and then you can aggregate them. Of course, you have to be careful. If you have a hash bucket and you're doing hashing based on name, there could be different names as well together. For instance, Smith and Smith and Smith, but there could also be other things like whatever, John and John. And then you have to still be careful, depending on the implementation, that you take only these three, of course, to group Smith, and these two to group John. Okay, these are little things to consider then, but in principle, sorting and hashing works for both. And then projection. Projection is trivial to implement because what you have to do there is only to drop some of the attributes of the tuples. The only thing where projection is not trivial is the case when you're writing select distinct, because select distinct would require duplicate elimination, and then you have to go back to what we just discussed on how to implement duplicate elimination. Yeah, that's the end of the section on implementation of operators. So we have seen that for most of the operators, we can think of multiple implementations using an index, using not an index, using hash join, nested loop join, merge join, and so on. And depending on the implementation, and of course the data and the predicates, these different implementations come with different costs, right? So the decision, should we take this implementation or this, comes at a different cost. So runtimes are different. And sometimes even it matters if we have a join R and S or S join R. Result-wise, these are identical, but for the cost, this might not be the case. We have seen this when we computed the cost for the nested loop join, the block nested loop join. And again, I mentioned this already a couple of times, the implementation can be used perhaps not if there's no index available, for the index-based nested loop join and so on. And all of these considerations have to happen before the query is executed. So this has to be decided when the query comes to the system. Then the database system has to now see all of these implementations available, and index structures available, and data statistics. And then in the end, we have a query plan that consists of multiple operators, and the database system hopefully has decided for the correct choice of operators, for instance, nested loop or an index-based scan here, and so on. And then it can be executed, and hopefully this will lead to a fast execution of the results. And of course, I think it should be kind of clear, but no matter which implementation and which order of the join, the result is always the same, right? So if a query is posted in SQL or in relational algebra, there's only one interpretation of what the result should look like. We're only talking about different ways how to compute it, but the result is always the same.